Hey, ladies and gentlemen, I'm going to try a little something different. I found a new button on my screen recording thing that allows me to put a video of me alongside of all of this. So I thought maybe it might be helpful if you could actually see me doing the problem along with looking on your screen to see everything going along too. So maybe it'll work, maybe it won't. We'll see what happens. Today is 8.2 part 2, which is moment of inertia. And you know, we've talked about inertia before. Inertia is how hard is it to start or stop something moving. Like a really large person has inertia. It's hard to get them up to speed, and it's also hard to stop them once they're up to speed. Moment of inertia is the same thing, except instead of moving in a straight line, it's spinning. Some things are harder to start spinning, and some things are harder to stop spinning. And they're all, it depends on their shape. It depends on, number one, their shape, and how much mass and where that mass is located. So shape, how much mass, where the mass is located. So I just wanted to start this off with a video that I found, and it's called "Kid Gets Owned by a Mushroom." And these are like classic playground. I don't know if any playgrounds that I grew up with had anything like this, but this thing has a ton of rotational inertia, which you're going to find out. This is hard to start and stop moving. Like, this kid grabs a hold of it and gets thrown. Like, it is once this thing gets going, it's got so much mass. His little body is not going to even change that in the smallest amount. So it's kind of fun, but it just goes to show you that spinning things, human bodies aren't really all that much when it comes to it. So we've got 1, 2, 3, 4, 5, 6 different shapes that your book goes through. A ring that's has no width, a cylinder, a sphere, a rod spun through the center, a rod spun on the end, and then some rectangular thing through the center. And you can find their moment of inertia by taking m, the mass, times r, the radius squared. So this is 1/2 mr squared, 2/5, 1/12, 1/3, and so on. And your book has an example here. It talks about using your physics book. Like if you were to spin this thing, I don't have a physics book, but I do have, well, spinning it like this is a lot harder to do than spinning it like that. Even though the mass is the same, it's really easy to do this compared to doing that. So moment of inertia. This has a larger moment of inertia than this does, and it's kind of mimicked if you look over here. Spinning something around the end is 1/3 ml squared, around the center 1/12. So this is much easier to start and stop spinning because of the 1/12 versus the 1/3. Moment of inertia. How hard it is to start and stop things spinning. Your wheels, like for instance, like bike wheels. I remember, like, I was a big biker in college, and the single greatest thing you could do to make your bike faster is better wheels. And I know Rolf made really great wheels, so I just looked up Rolf wheels, and I looked up road wheels, and we'll get, like, there's all different types, alloy wheels, carbon wheels. We'll get the top of the line just so I can show you. So these are wind cutting spokes. It's really lightweight carbon fiber, really, really strong. And no joke, you look at these things. Let's go to the specs here. $2,400 for these 2 frickin' wheels. Like, wheel technology is really big money. Like, to be able to get a wheel that can support a human being but zip down the road at like 35, 40 miles an hour, and make it as lightweight as possible, big buku bucks. Another thing, like your truck. I like to lift my truck one day. Putting bigger wheels on a car, it saps your gas mileage because it's harder to start the wheels spinning, and once they're spinning, it wears on your brakes more. It's harder to slow them down. So putting bigger wheels on a truck will really take away what little gas mileage it had to begin with. So here, let's do a couple of problems. The first problem, it says moment of inertia. A simplified model of a twirling baton is a thin rod with two round objects at each end. The length of the baton is 0.65 meters. So here's a baton, and then they're saying it's 0.65 meters in length. The mass of each object is 0.3 kilograms. Find the moment of inertia if the baton is rotated about the midpoint. So we're going to rotate it around the midpoint. And what is the moment of inertia if you rotate it about one of the ends? So let's do that. A thin rod, 0.3 kilograms. Find the moment of inertia. Okay. So what we're going to do, we're going to first find the moment of inertia when you do it around the center, and then we're going to find the moment of inertia when you do it around the end. So the moment of inertia when you do it around the center, we're going to look back here, and we're going to treat these as point masses. So we're going to go back and look up the moment of inertia for a point mass. It would be like this right here, mr squared. So this is a point rotated around a single radius. So the moment of inertia is mr squared. So part A. So the mass is 0.30 times the rate. The radius is half of that. So 0.325 squared. So bring up my calculator. 0.3 times 0.325 squared, and that's 0.032. Now that's kilogram meters squared. Now that's just for one of them. Because I have 2 point masses here, I've got to find the moment of inertia of both of them. So that'd be 0.064 kilogram meters squared. So that's what it is around the center. So part B, so we'll call this the center. What if we rotate this thing around one of the ends? What we're going to do, we'll treat it as a point mass again. So the point mass, so it's going to be the exact same equation, 0.3 times the radius. Now the radius in this case is 0.65 squared. So I take 0.3 times 0.65 squared. And I get 0.13 kilogram meter squared. Now I only have to do the one mass here. This one, since the point is on the center of rotation, we're just going to assume that the radius, how far away it is 0. So it doesn't have a moment of inertia because it's a point mass. It's not a sphere. It's just a single point, and it's on that. So this has, if you look at it, this is like twice as large. Spinning it around the end versus spinning it in the middle, this is twice as easy as that one. Another example that we've got is Newton's second law. Newton's second law that we all know is F equals ma. Now for rotation, it's a little bit. It's basically the same thing. So Newton's second law for turning. It's very similar to this, except I'm going to use the force to turn it, and it's the mass times the angular acceleration. So I have all special like things for this. And the force, there's a force that turns objects. We call it the torque, the Greek letter tau. Now, when you push on something in a straight line, it only depends on its mass. When you turn something, it depends on its mass, or its shape, because its shape dictates where the mass is located. So what we do is we call it the moment of inertia. We're going to draw back to, instead of just the mass, you have to use the moment of inertia, all of these guys, because it's not only dependent upon the mass, it's dependent upon where the mass is located. And the acceleration, the angular acceleration, is this. So I know that your book will write it like that, but I prefer it actually like this. I mean, I can make it look like that. I just solve it for the letter alpha. So alpha equals torque over moment of inertia. And that's where they get it from. I like it like this because F equals ma in the rotational world. So here's an example problem of that. A solid steel wheel. So I'm going to draw myself a solid steel wheel here. Has a mass of 0.115 kilograms and a diameter of 0.44, so it's got a radius of 0.22. It starts from rest. You want to make it rotate at 8 revolutions per second in 15 seconds. Whoo! What torque? So we're gonna pull on this thing on the very end with some force. The harder we pull on it, the faster it spools up and starts spinning. So let's figure this out. I'm going to use Newton's second law. Torque is equal to moment of inertia times angular acceleration. Holy cow. Part A says what torque? So I know I'm looking for this, which must mean that I know the moment of inertia. I'll color code these things just to make it a little bit easier. So moment of inertia. So I'm going to look for these separate, and I multiply them together, and I'll get to how much torque. Moment of inertia, first of all. This is a solid steel wheel, so I'm going to go back here. A solid steel wheel is this one right here, 1/2 mr squared. The mass is 15, and the radius is 0.22 squared. So that actually was pretty easy. So 1/2 what's going on? 1/2 times the mass times the radius squared. And I get 0.363 kilogram meters squared. So 0.363. The angular acceleration. That's my change in velocity over the change in time. And they give me that, the change in velocity over the change in time right here. Oh boy. First of all, 8 revolutions per second. I have to make sure that I do that in radians per second. Jeez Louise. So 8 revolutions per second. One revolution is 2 pi radians. So this comes out to be 16 pi. So 16 pi is 50 radians per second. So my change in angular velocity up here. It goes from 0 to 50. That's the change in angular velocity. 50 radians per second. In 15 seconds. So divided by 15. It's making a video. 3.4 radians per second squared. So I take that number, put this guy in here. So now I can figure out how much torque it takes to do this. So I take